Thank you all for coming. It's very kind of you to hear me, or some of you to hear me for the third time. I can hardly take that myself. But with some nervousness because of the introduction, and thank you for the kind introduction, I'll tell you, but you're to forget this immediately, that I went about 15, 20 years ago to give a seminar in Bristol, where Philip Drazen was the professor. He's been mentioned a number of times. I knew Philip quite well, and he gave me an introduction pretty much as has been given, and said, Herbert came in 1968 to Cambridge. That was 35 years ago. He came for a year and is still here 35 years later. And then he added, you might bear that in mind when you hear his mathematical calculations. I was not pleased. Anyhow, I'd like to tell you today about how long it takes to get there. And the idea is we're going to talk about similarity solutions that are always, or not always, often very useful. And the point is that we have some nonlinear differential equation. Where's the pointer? Oh, on the top, right. I put it there purposely so I wouldn't forget it. Similarity solutions, and we'll consider some nonlinear operator which is dependent on some vectors x, spatial vectors x and time. The dependent variable I write as a capital psi, and of course the operator may well depend on the independent variables, the position vectors and time, and a whole series of parameters. I've made this bold on purpose because there are lots of parameters possible. And now sometimes you can get a variable which is dependent on x, t and p, all the x's, t's and all the p's, such that instead of this nonlinear operator on x and t, this is another generally nonlinear operator but just on eta, and it operates on f. And the simplest example I can tell you about, which you know is TT, is kappa TXX, the diffusion equation, and then eta would be x over the square root of kappa t. That's non-dimensional, and instead of having this complicated two derivatives equation, you might just have a simpler one derivative equation in eta. That's called a similarity variable, and it sometimes, not always, reduces the partial differential equation to an ordinary differential equation, and when it does that, of course, it's much easier to solve. This is much easier to solve as an ordinary dE in eta. But now there are initial conditions associated with this, and boundary conditions, and in general, the initial conditions are not satisfied by this similarity variable, because this is not useful when t is equal to 0, so you can't apply initial conditions. So the similarity solutions you get, which is the solution of that, have got to be independent of those initial conditions. Now, how long does it take if we get the real solution of this to be in good agreement with the similarity solution? How long does it take for the real initial value problem to approach this similarity solution? And that's where the title comes. How long does it take to get there? And I'd like to do a little experiment, which I don't think you'd see from there, so I'm going to put this on, and the experiment is going to be on this blue area, right? And what I've done is I've stolen from the hotel some wonderfully Newtonian fluid. It was wonderfully Newtonian fluid. It's such wonderful fluid. It says here, Newtonian, kinematic viscosity 3.17. The only problem is, it doesn't have the units. It just says kinematic viscosity 3.17. What's the use of that? And I thought especially for Jim, but he's especially he comes just at the right time. I was just saying, this fluid has a kinematic viscosity, it says here 3.17, but it doesn't have units. So I assume, especially for you, the units are acres per fortnight, because no American knows what any of those or either of those two mean. But every Indian, I hope, knows what an acre and a fortnight is. Right, now it's brand new, as you see. There are no tricks here. I've never done this before in my life. I'm pulling it open and I'm going to pour out some fluid, and I'm not doing it very well. You know, I'm zigzagging. I hope you can see that here. And even before I finish talking, it's really quite circular. So if there's a similarity solution for this, we'd imagine that it was approached quite quickly, because no matter how non-axisymmetrically I drove this out, it still was rather axisymmetric. But how long would it take? What if the initial solution, the initial conditions, was a constant volume of this size and shape, this size and shape, this one, not allowed to crumble, this one, well, I first should have shown you this one, which is like that, this one, which touches the surface, and this one. Which of these reaches its similarity solution most rapidly, and how rapidly? I filled each one of these with 3.17 acres per fortnight fluid and lifted this up. It'd be much more than I had there, but how long would it take? Would you be here for the weekend, forced to look at this before it reached the similarity solution? That's what this talk is about. So back to the talk. Where are we? Now, I've talked about rather small blobs, but here's exactly the same experiment, well, sort of experiment, that happened in 1919 in Boston. There was a huge tank that held molasses. Molasses was used, I think, only by Americans to make in cooking. And in January, on the 14th of January, a boat came in and filled this tank up to the very top with molasses. What it didn't know is that the sidewalls was getting rather weak, and there was a bit of a tremor apparently, and it broke down and it just spread the molasses everywhere. Just like this. It was no different to what I showed you here, except in scale. Of course, the scale was very different. It went out at 35 miles an hour, and I assure you that's not as fast as this went. It killed 21 people and quite a few hundred horses that got in the way. As you see here somewhere, you can see this horse going to be inundated. And it said that for quite a few years later, you could smell molasses in the streets of Boston. Well, how long did that take to spread? How long did it go before it reached approximately a similarity solution? This is another example. These are the domes on Venus, which are something like 10 or 15 kilometers across here. They're formed by magma flowing out exactly like this. But how long does it take before that gets to a similarity solution? And why that's important is, if you make measurements of this dome, that wasn't done in Venus, but in other places it was, as a function of time, you can evaluate the viscosity. And that's what you really want to do if you believe the similarity solution is right. Here's another example, Olympus Mons on Mars. It's 625 kilometers in diameter, a little larger than this, which would be hardly 625 microns. No, it's more than that. 625, well, units. Units of length. It's exactly 625 now, and it'll. So here's this large magma dome. It would cover almost all of France. That's the size it is. Now, I'd like to show you an experiment that unfortunately I can't do here, which is what happens if we rotate this, rapidly rotate it, and I'm going to show you a video of such an experiment which we did just a few weeks ago, and there are lots of questions that you can ask and I can ask, but I can't answer because I've just done this recently. So let's see the movie, and it's sped up by a factor of 100, and it's going to take about a minute, so you're seeing something like 2 hours worth. Oh, you're not if you... Come on. Oh, it's not my day today. There you go. Yeah? And it's unfortunately a stationary camera. We don't have yet had time to make it co-rotate, but you can see it's rotating along, and you can see that from the little rubber tubings there. And it's sped up by a factor of 100, so we've mostly got 3 or 4 minutes here or something like that. As you see, spreading, but not quite as axisymmetric as you might see. Well, you will see there. And you can already see that it's not axisymmetric, which must be due to the rotation. That's the only thing that's different. And in this case, there are 3 definite arms that come out in long fingers. So far, we've only done this experiment about 3 times. This is once, when it had 3 fingers, then we could get 4 fingers, or just 2 fingers, depending upon the rotation rate. And there must be a wonderful problem which I'm going to do, not giving this away, of how at low Reynolds number and low Rossby number, it's rapidly rotating, this becomes unstable. Okay, well, the contents of the talk are going to be the experiment and the introduction, which I've already given you, and then I'm going to tell you the adjustment times, how long it takes to get to the similarity solution for constant volume releases, i.e. if this was fluid and I lifted them up and let the volume go out. Oh, here's another example. Don't need this anymore, so I'll get rid of it. So here you can guess, this is probably the smallest volume, the largest volume, which approaches its similarity solution quicker. Here's the thinnest one, which approaches its similarity solution quicker. Well, that's what we're going to talk about. And then I'll say something about change in flux, and I wrote that in a slightly smaller form because I may have run out of material, or time rather, and I won't say as much about that. Getting muddled where I am. Okay, well, this is what I said to you before. We're going to consider general nonlinear problems, look at similarity solutions, and see how long it takes to get there. Now, time is important. This is an example. In England, this woman has come to the bus stop, and she asked quite reasonably, what time is the bus due? And the answer is November. That's, you know, she was hoping it would be December, but she's going to have to wait for quite some time. So time does play a role. I could say I got this in March from a wonderful English magazine, and of course I gave this talk last month. This was useless. Nobody understood what I was trying to say. We'll start with a low Reynolds number current, which we had here, and I'm going to do this again in the actual workshop. We have, everything is axisymmetric here. We have a blob that spreads. It has a 0 velocity because of the no slip condition at the base. 0 shear, because we'll imagine there's air here. 0 shear at the top. There's an unknown free surface. We want to know how h varies with time and with radius. And there's a constant volume v. And what we want to really know is how rapidly it spreads. So what Rn is as a function of time. Now, gravity is downwards, and it forces a horizontal motion. It's quite interesting. Gravity is there, horizontal motion. I guarantee you there'll be no horizontal motion if I drop this. But here, it's different. There is horizontal motion because there is a horizontal gradient in the pressure. The pressure here is larger than the pressure here, so there's a horizontal pressure gradient, and it makes it spread out. The pressure gradient due to the weight of the overlying fluid is resisted by the viscous stresses. This is the radial pressure gradient. P is rho GH, so dP dr is 1 over rho is GdH dr, and that's resisted by the viscous stresses, and we'll forget about the radial component because this is a thin blob, as you saw here. So that's the equation. That says that the velocity profile looks as I showed you here, and that can't be right at the nose. The nose is something very special because where the rest of the fluid, forget about just the front, goes along like this, the nose actually collapses and goes like that. But now the idea is the nose makes no difference at all. You just take into account what goes on from here to here, and that tells you what goes on. So this is the velocity profile, but not at the nose. Then there's local volume conservation, and we've met that a number of times already this week, which says if there's more fluid that comes in here, a bigger flux than comes through this vertical surface, then the difference in flux has to be taken up by the surface rising. Well, it really goes the other way around. The surface drops down, but that's all taken into account here. So when we put that all together, we get this nonlinear partial differential equation in T and in R, and G the gravity and nu the kinematic viscosity, 3.17 acres per fortnight. And then we have to conserve volume, so we have this volume conservation relationship. Okay, well that's the nonlinear differential equation. Here I've written it down again in terms of beta, because it's G prime, really G if there's air on top, but there could be some other fluid there, over 3 nu. So there's one parameter here, R and T, nonlinear because it's h cubed dH dr. The front is equal to 0 at the front, and the conservation of volume is here. Now there's a similarity solution which goes beta v cubed to the 1/8 t to the 1/8. Forget about this 894, that's just to allow the similarity variable, eta, which I've written like this, to go between 0 and 1, if I make z rather go between 0 and 1. Here's the eta, so this is the equivalent of this x over root kappa t, and then I've just normalized it so that the variable z goes between 0 and 1. So there's the similarity solution. And what's going to be of interest is when it looks like this at some stage, to take this slope, h at 0t against Rn of t, and I'm going to call that gamma. That's h at 0t over Rn of t, and I can calculate that from the similarity solution, and it goes down like t to the minus 3/8. Okay, now as it says here, I developed this in 1982, and nobody in the Department of Applied Mathematics believed a word of it. They all said, Herbert, you're so incompetent, you don't realize that it's totally driven by the front. What goes on at the front, which you've neglected, plays the major role. To which I said, you're totally incompetent. A little firmer than that, but I won't repeat what I said. You're a little incompetent because you don't realize that in a viscous flow, the front plays no role at all. As long as surface tension is sufficiently small in that regime with a large bond number, it's just that plays the role. To which some of them then said, you're a complete idiot, Herbert. If you only read a paper by Huppert 6 months ago, it says exactly that the front plays the major role. You don't even read your own work. To which I said, that's for high Reynolds number. That's a totally different situation. This is low Reynolds number. Anyhow, they argued so much with me that I thought I'd better do some experiments. And here were the experiments. Here's the radius appropriately non-dimensionalized. Here's time going up to almost a month, and here's the first reading after 10 seconds, and there are a whole series of different experiments here. Different initial conditions, different volumes, different viscosities, and it all falls much to their annoyance, on this line. In fact, I made matters worse, and I realise now I made a mistake, that after a few days when it was going so well and so slowly, I only had to make a measurement once every other day or so, and that was increasing it. And I used to do that before going down to tea. I'd work on something else during the morning, then I'd go down to a tea, or I'd make a measurement, then I'd go to tea and I'd say, it's terrific. You know, it fits just perfectly. You guys who said I was stupid are really wrong. After one experiment that went for about 2.5 weeks, I again said, it's terrific, it really goes wonderfully. And a colleague of mine said, you know, Herbert, I have the feeling that tomorrow's reading is not going to fit at all well. And I understood what he meant, and I stopped the experiment. Okay, so that at least works. But how long does it take to get there? Time is really important. How long is forever? Lewis Carroll has his rabbit in Alice in Wonderland say, how long is forever? Sometimes just a second. And why I think you always have to have non-dimensional numbers. How long is a second? If you're with your partner, 1 second may be over so quickly you miss him or her. If you're sitting on a hot stove, 1 second is forever, and you don't want that. So it's really important to know what time is. Now I have my own view, slightly different question. How long is long enough? Sometimes a lifetime is needed. Now, nobody under the age of about 40 will understand what that means, but well, no, some of you, I'm not going to point out, who are over 40 knows that sometimes it's only at the end of a life that you really understand what time is, but some of you will know about that in 60 years' time or so. Okay, so we did some numerical integrations, and we started with a circular cylinder, the simplest case. Well, this case here, forget about the rim here. This case here, numerically, so it starts here at t equals 0, t equals 10 to the minus 3, and finally it comes like this. Here's the radius non-dimensionalized. The numbers don't really matter, but you see it's beginning to look as the similarity solution. But how long does it take to get there? Well, now if you divide radius by beta to the 8th for different values of beta, this is the similarity solution that starts at 0, because you've got the t on the bottom here. You normalize it by beta to the 8th. Here's the similarity solution. And now here is the solution of this for different values of beta. So you're just changing that parameter, and you see that they all approach the similarity solution, but for smaller beta, 0.1, it takes longer to get there. So time really makes a difference as far as beta is concerned. Now, how will we work this out? And with no apology whatsoever, guess what I'm going to use? Dimensional analysis. And it's going to work, Ishan. Otherwise I wouldn't give the seminar. You have beta, which has dimensions L to the minus 1, T to the minus 1, and the volume, which has dimensions L cubed. Now that says the only time scale is 1 over beta V to the 3rd. So what that says is the time, tau, to get to the similarity solutions must go like this, because it has to have the dimensions of time and some function of the shape. There's no doubt it's going to be different if it's a rectangle. You know, the biscuit is going to go, well, maybe that's not a good example. This is going to go different to this, that I can assure you. It'll depend on the shape. It'll depend on the orientation of it. This biscuit, if it was the same volume as a cup, that would make a difference, because this is a thin, that must play a role. The shape, and I'm sorry I've left out of here, and I tried to fix it in the last minute but couldn't. P, which is the percentage agreement. We're just going to take the simple case of the radius of the numerical solution and the radius of the solution, and we'll compare them, and P is the difference. Okay, so P should be in here. Clearly, initially, The similarity solution starts like a delta function, and so the agreement is lousy with the actual solution. With time, you hope the two will be the same, so the time to reach 1% is going to be considerably longer than, but how much longer than the time to reach 10% and so on. Okay, so the time scale is going to be of that form. And now here, either you can look upon this as a test of the numerical calculation or the test of dimensional analysis. But here's the time as a function of p. This is the radius to within 15%, 10%, 5%. And you see there's a 1:3 relationship as we vary the volume for a circular cylinder. It takes longer to get to within 5% than for 15%, just as you'd imagine, and the curves would go up and up if I wanted to have 1% and 0.1%. Okay, well I see it as a check on the program. You can see it as a check on dimensional analysis if you like. Now we'll have a look at how it varies with beta. It's meant to go, the time is meant to go like the inverse of beta, and you see that's exactly what happens. And again, if you want to be 5%, it takes you longer than if you want to be 15%. And these numbers are, well, irrelevant really. They just detail how big it is here. Now I thought, how does it vary with gamma naught, this other parameter? And gamma naught is h of naught naught over the radius at 0, the actual. So that's the initial value of gamma naught. So the gamma naught of here is the ratio, the aspect ratio of this height to this radius. Of this one, it's this rather small height to this radius, and so on. And so I did it for the circular cylinder. It's a damn lie. My wonderful summer student did the calculations, and I saw them. So it's not that I did it, she did it. She's terrific, and I'll show you photographs of her later. Because I want to know how it varied with gamma naught, and much to my surprise, it was almost the same. It was 8/3, as I've sort of written here, gamma naught to the 8/3. And I was really perplexed about that. I thought it would be much more complicated and surely must depend differently for large gamma naught, small gamma naught. Why isn't? I didn't understand that. So I had her do the calculations. Oh, sorry, and here's the result. That's, I've already shown you this slide. For the initial cylinder, again, the numbers don't matter, just how close you want to be. Gamma naught, there should be a naught there, I'm sorry, to the minus 8/3, but the beta v to the 1/3 dimensional analysis we've shown to be correct. So I had her do it for an ellipsoid. So it's an ellipse that's rotated around, and again it was the 8/3. And I thought, I thought an ellipse would be totally different, or a hemisphere. And then I realized, oh, well, here's the relationship for the initial ellipse. Different numbers, but still this gamma to the minus, or gamma naught, sorry, that's missing, to the minus 8/3. So I thought, guess how you must prove this? What? You said it last time. Of course, that's all I know how to do. You make a normalization with h naught, the initial height, r naught, the initial radius, time as you've been told to do it, and you get this relationship here. It's gamma naught to the 8/3 appears there. We haven't yet said anything about the shape. So it says any shape will go have a time scale that goes like gamma naught to the minus 8/3. That's, I think, really quite surprising. It doesn't matter which shape of these you take, it's only the aspect ratio and the volume that play a role. But there must still be some difference between these shapes, and we're going to have to find them out, and we will find them out. This is now a cossoid, as I call it. Everything's axisymmetric again. And here's the cossoid, oid because it's axisymmetric. It comes like this. This is what it is initially. And what you see at the tops here, for a rather smallish time, it begins to drop down. But here, for smallish times, it doesn't do anything. It's not until this has dropped down half the way until this really begins to move. So what's that saying? That where, I'll do it on here, where it sits here and has not only a zero, but a zero derivative in the cossoid, it moves very, very slowly. So details like that will definitely play a role. The cossoid will not be the same as this character here. But it will reach the similarity solution. It'll just take much, much more time. How much time, we're going to work out in a minute. Okay, now what about the difference between the numerically evaluated nose and the similarity nose? The similarity solution starts as a delta function, so it's always, in this case, behind this spreading out blob, because it starts as a delta function, i.e. it has zero radius, and this guy spreads at time t equals 0, just as the delta function does, the similarity solution, and he always beats the similarity solution. So you can consider the difference between the numerically evaluated, the correct radius, minus the similarity solution radius, as a function of time for different values of beta. And what you see is the difference between these two goes down like t to the minus 7/8. Not at the beginning, this is the large time asymptotics. Now I could give you 2 or 3 slides of proof, but I don't want to do that. Let me just say you can prove that properly. What I'm just going to do is use it. It says that the difference in the radius goes down like t to the minus 7/8. The similarity radius increases like t to the 1/8. That says the accuracy, the percentage error, which is given by the difference between the numerical solution and the similarity solution, normalized by the similarity solution, because I have a relationship for that, goes, well, 1 on t, but that's got to be tau, the time scale. So the difference has to go like tau. So that says that tau has to be inversely proportional to p. So for this problem, it says that if you want to be 1% accurate rather than 10% accurate, you have to go 10 times longer. So what that says is, I've already shown you the beta v to the third, gamma naught to the 8/3, all of that to the minus 1. I've shown you that. There's an A, and A must depend on the shape. This guy is going to be different to this guy, even more different to this guy. We'll have to work that out. And then it's going to go like that, and then there's the 1 on p, that's this relationship here, and then it's going to go like 1 minus epsilon p. Now here's some values of A and epsilon in this relationship. Let's start with the circular cylinder. A is about 3 almost. Very small epsilon. Let's look at the extended cossoid. The A is 26.3. That's the well, not the smallest, but the largest and one of the smaller ones in this table. Here it is. So what we're saying is an extended cossoid of exactly the same volume and same initial aspect ratio will take something like 9 times longer to reach the similarity solution than will a circular cylinder. Here's a cone, which is the smallest one on this list, and it looks like this, and so it's spread out and it can go fairly rapidly. That's the smallest A. An inverted cone does the exact opposite. An inverted cone looks like this, and it's 0 at the base, and that doesn't want to go at all, move much, and so that has a much larger value of A. All of them have small values of epsilon. Why that is, I don't know, but it is interesting. What the largest value of the initial A I think you could just have something that is not only 0 in the middle, but its derivative is 0, and second derivative, third derivative, and I think that would, so it would go on forever. You can make A as large as you like. The smallest value of A has to be the delta function itself. If you started with the delta function, it's at the similarity solution, but that's a very special case, and then A would be 1 and epsilon would be 0. Okay, now what about in real life? Well, in real life, beta is 30, v to the third is 7. The time scale is very much less than a second, and it took, as you saw here, quite a few seconds, and also in the experiment, to set the system up. The first measurement was after 10 seconds, so it was already really quite accurate, as you saw on the graph. On Venus, it's something like 300 years to reach the similarity solution, and on Mars it's something like 3,000 years. And this is a paper which I hope will be finished with Thomasina Ball, my summer student. So let me tell you a few other problems. This is a one-dimensional viscous current. It's one-dimensional, so we have x here. It's still non-linear. There's still one parameter. The same thing can be done. You can have an axisymmetric current in a porous medium, still non-linear, still a parameter here in terms of the permeability and the porosity of the permeability, and a one-dimensional current, and that's being done with a wonderful summer student. And there must be lots of other problems for which this can be done, and I do know a few, and that's part of the reason why I've given a few seminars in the last few weeks to various people who said, oh yeah, I can think of how to do this. Now, here's an example of T properly normalized, or tau it would surely be, properly normalized with beta, so it all falls together, against P, the accuracy, the percentage accuracy. The only way you can get totally correct is if you go forever. But if you want to get to within 5% accuracy, then for a specific volume, tau beta is 0.3. And this must go further along like this, because the accuracy at the beginning is very small, because you have a delta function, which is the similarity solution, and you have this whopping big radius, which is the initial value. So there's no agreement between them at all. But what if you slightly change the problem, and instead of saying at time t equals 0 the similarity solution goes and this bucket goes, what we said is let the similarity solution go and get to the edge of the bucket, and then count that as time t equals 0. Let the two of them go at the same time. So the similarity solution doesn't start before, inside less radius than the bucket, but we give it a chance. It's like a race between two people, but one is quicker than the other, so you give them a handicap. Well, we'll give the bucket a handicap so the similarity solution isn't so disadvantaged. Well, then you could do the same thing, only starting it off differently, and this is what you get. Initially, it's got to be perfect. They start together, so for 0 time, there's got to be 0% error. Then it's going to increase, because the bucket, it has more shape in this way, runs in front of the similarity solution, and it gets to about 4.7% in the case of a circular cylinder, and then it begins to go back again. It has to go back to the same curve, because after a long time, who the hell knows what really the initial condition was in this little start that you gave it. But so you can change the system from being very inaccurate initially to being perfectly accurate initially by defining initially properly, and then the accuracy will increase and then decrease. This shows you the same thing, only on a larger scale. that it's 0 for very small time. It comes up to about 4.7 and then goes back again. I could show you this sort of curve for all the different initial conditions and bore you to death, but I won't. Let me just say that they have different maximum errors. Some can go 10, 15%, depends very much on the shape. Here's now just an example. Here's the numerical solution that starts at 1 and with time goes along like this. Here's the similarity solution, which at time t equals 0 has a 0 radius, and that should be an r, I don't know, it's got to be an x, and comes along here. That's the similarity solution, and this is the early started similarity solution. So you give the similarity solution some time to catch up with the circular cylinder. So at time t equals 0, they're exactly the same. The numerical one, this one beats the similarity solution, and so the largest disagreement is about here, 4.5%. It gets less and less, and you see that at all times it's a better solution than this similarity with this one. The green is always better than the blue, and it's always behind. They squash up together, so in the end, for a very large time, they'll all be the same when they've forgotten the initial condition. So a summary is you can work out the similarity solution, how long it takes, using dimensional analysis. Well, often you can do that, I hope that, and occasionally using some theory. And for an axisymmetric viscous gravity current with constant volume, but there are a number of different problems that can be done, the relationship looks like this, and I maybe should have added divided by p, the percentage error, and it's it's considerably less than a second in the lab, and about 300 years for the Venus domes. And it's now 4:45, a wonderful time to have the 5-minute break that we talked about, while I take a breath and you will do whatever you like.
That unsteady conduction problem, right?
Just as a simple example.
So is there an equivalent of whatever you said there? It looks like there the early time solution exactly agrees with the...
Well, here we're...
similarity solution exactly agrees with the full solution.
You'd have to, it's a different similarity solution and different equation, but it's the same idea that would work here. What if I suddenly impress a temperature on the boundary, for example? What will it look like with time? How will it build up? And that'll make a difference whether I suddenly impress it or slowly impress it. For a long time, it surely doesn't make any difference whether I impress it at 5 degrees or, it take 5 minutes to bring it up to 5 degrees, or I do it instantaneously at 5 degrees. The temperature profile from there will look exactly the same, 5 here and then by diffusion. But how it'll get there, that similarity solution, the long-term solution, will depend upon how quickly I make up the temperature. That's an example.
Usually we start off with a sudden step increase, right?
Usually, but you don't have to.
Would that create...
I bet you don't start off like that in the lab.
No, no, but you know, if you do an exact separation of variable solution for a finite boundary, and then you do a early time similarity solution, both these match at early times because the other boundary is far enough, right, for a sudden step jump.
There must be situations, sure, where they'll match, but there are lots of situations where they don't, like this one here.
Okay, so...
And please. No, yeah, the audience can talk to each other, that's all right.
On a semi-infinite rod, if the rod is initially at temperature 0 and you bring the left edge up to a non-zero temperature instantaneously, it happens that this problem exactly matches the similarity solution. But you could have other conditions. For example, you could have the left 1 centimeter of the rod at temperature 1 and then maintain 1. And then, over a long period of time, it will still match that. But the initial transients.
Yeah, well, that's what I say, how quickly you bring it up.
When you say the classical problem, you are referring to a problem that you are familiar with. But there are other problems.
I'm not pretending I've solved every problem in the world like this.
I have a question regarding the time.
Sorry?
I had, sorry.
No, no.
Uh, instead of matching the instant of time where the similarity solution reaches the radius of your initial fluid blob, just a very small comment. If instead you tried to find a time difference such that the long time asymptotics were as precisely matched as you could match them, then your characterization of the shape would reduce to one quantity which had time.
I don't, well, I do think I have understood you. I don't think that would make a difference, because this part, no matter how you start it all off, this is exactly the same. And you're saying, would it be possible, I suppose, would it be, you're asking if this curve could come here or something like that?
If you go to one of the other curves where time is on the horizontal axis.
Yeah, time is on the horizon. Oh, wait. Say this one or?
No, one of, the one where it shows the approach and you have.
Oh, here.
Right. What I am asking is, in the lower graph,
Yeah.
can one of the curves be shifted horizontally so that the long-term asymptotics matches?
But see,
and, the first error term is made zero.
Well, one sec. These two curves at infinity will be the same.
Yes, but there is
But-
an error term.
But if
and
I,
there is a series.
but if I lift this up somehow so that it's I can't change this one. That's the real curve. If I lift this up somewhat, and we'll talk about that in a sense a little bit later, it will cross over. But it could be, well, of course, you could.
The asymptotic behavior for both is the same. The
Yeah.
leading order. And there is an error term, but the error term also has an asymptotic expansion.
Yeah.
And you could try to, what I'm asking is if you could shift it horizontally so that the leading term in the error becomes zero. And then you would still have other terms. And that would sort of give you a unique shift that you need. I don't know.
I don't know either. That's an interesting question, and I'll have to think about it. But let me ask a well, I don't know whether this is slightly different or exactly the same question, only put in different ways. I could calculate the area under this curve at any amount, and now you could ask, and I can definitely do it when it's finite, how could I lift this up or change the time so that I minimize the area under the curve? That's another way of looking at the error. So what I'd do is I'd lift it up in such a way, I'd bring this back in time in such a way that it crosses over and there's just as much above the curve as below the curve. Well, I think I'm going to say to that, I've taken a somewhat arbitrary definition of what the error is in just taking the radius. I'd get different results, and I haven't looked at it all, if instead I said, let's have a look at the area in some sense. What's the area covered? That would be different because it's r squared. The volume has to be the same because there's conservation of volume. I could just look, well, the height would also be the same. I'm sure you're right in the general sense that there must be different ways of starting the race to make it all equal. Or to put it another way, what you're saying in general terms, if I use the argument of the two people, one who runs quicker than the other, I could change the race so that I say to one of them, go a little more slowly at the beginning, and then asymptotically you'll be in the same place. Yeah, I bet that's possible, but yeah, this is the simplest, I would say. Yes?
I have a question.
Then come out with it.
Yes, okay. So it was regarding the relation between tau and gamma.
Well, that's so.
Yeah, I know it's a straight.
Tau goes like gamma naught to the minus 8 thirds.
Yes, but does that graph really shows there was a plot
Yeah.
between gamma and tau. So I
Yeah.
think it was more of a linear solution. So first of all, my question is how how are you arriving at gamma is equal to minus 8 to the power 3? And what does gamma mean? Because gamma is actually h divided by r to the power n. So what is the essence of this term? Because my tau will be a function of gamma, right? Like the tau,
Yeah.
the time scale, is a function of gamma.
No, but I think what I'm saying is, say I have a constant volume V and a constant beta, right, and a constant shape. So we'll make it just for simplicity a right circular cylinder because that's the simplest thing. Then the question would be, how would this compare to that? Now let's imagine these volumes are the same. I may not have drawn them accurately. How does this initial condition compared to this initial condition? It's the same shape, it's the same volume, the same beta. So, I haven't put in gamma naught, the most important one. It's the same volume, the same beta, the same shape, so the A has to be the same. But the gamma naught is different because the gamma naught for this one is that slope and the gamma naught for this one is that slope.
Depending upon the initial condition.
On the initial condition, yeah.
But my question also is like, how are you reaching to the point that gamma is equal to minus 8 to the power 3? Like,
Oh, what I'm saying is, when you look at these two different shapes, if you non-dimensionalize the differential equation governing the similarity solution appropriately with this h and this r, you find it goes like gamma naught to the minus 8/3. That's the only thing that's left in the equation. So that's just saying what must be the result of that equation that's ht is equal to beta 1 on r ddr, whoops, h cubed hr. That's all, yeah. So what I'm saying is I can non-dimensionalize this equation with respect to the initial height and the initial radius, and the only thing that comes in is gamma naught to the 8/3 because that makes it ht equals gamma naught to the 8/3 beta h, well, the h's are now non-dimensionalized. I hope you understand that. H capital R ddr. So that just says that time has to go like gamma naught to the 8/3. Does that answer the question?
yes, it does. And the thing is, like you're talking about that, like there is already r in that. For an abstract shape, will that still go? Like gamma to the power minus 8/3 for an abstract shape?
Yeah, well, it depends on the differential equation. There's no physics involved in that. It's just saying how you can transfer the differential equation. Okay? Now I'm going to have to find where I am. But please do ask questions. Right. Now, so far, I've been talking about so-called direct problems. I ask a question. How long does it take to get there? That's asking the question and looking for the answer. There are lots and lots of direct problems. Let me give you one from geophysics, which is if I'm told that in Tokyo there's an earthquake and I know the structure of the Earth, how long will it be before we feel it here? And I can work that out, and that's a quite standard problem that was probably done in the 1920s. But there are inverse problems, and in geophysics that happens a lot, and they're much, much more interesting, which is you're given the answer, and you have to work out the question. So, if I say, oh, I've just felt a tremor, and I know because my friend in Tokyo told me that 10 seconds ago there was an earthquake there, took 10 seconds for it to go from Tokyo to here, can I work out the structure of the Earth? And the answer is no. There are many, many, many structures that I could devise that would mean it takes 10 seconds to get here. And even if I have an infinite number of earthquakes, well, an infinite exaggeration, a large finite number of earthquakes, I can't work out what the structure of the Earth is. Let me give you another example. Let me take 42, and poor old Ishan gets into trouble all of this time. If I say to Ishan 42 and ask him what's the question, he shrugs and he says, it's the number of the house that I live in. It's the number of girlfriends I've had. It's the number of cousins I have. It's how many days I could stand listening to you. The whole series, you can't tell. Sorry? 42, he says, is an exaggeration, what I thought. Yeah, 0. Anyhow, the most famous inverse problem, and I hope this will come over in India, but the most famous inverse problem is the answer is 9W. What's the question, the famous question, that leads to the answer 9W? No one's heard this, okay? Famous question, because there could be lots of one. Again, it could be the number of his house could be 9W, etc. It couldn't have had 9W girlfriends, I don't think. But so there's some answers that are cut out, but 9W could be lots of things. Sorry? 250. No, sorry. This is the point. I answer. I make the answer, and you have to get the question. So 9W. The famous question is, do you spell your name with a V, Herr Wagner? No, I can see nobody's got it. Sorry?
That nine is German.
Correct.
Yes, but W is not W in German.
It is 9W.
W.
Well,
You might have given it.
9W. He would. What can I do? That's the most famous example. Now, I'd like to ask some inverse problems. I've been doing all direct problems. I know how I start. I know what the stuff is. And out it goes, can I calculate it? I've shown you that. That's, as I've written there, the direct problem. I'm given the viscosity, the gravity, the kinematic viscosity, the initial shape, and then I determine everything else. We can do that. Now, the inverse problem is somebody comes down to the lab and you let him or her have a look. What if he's just allowed, let me just say he in general, if he's just allowed to look at the spreading drop, what can he work out? So you give him the answer, here's the spreading drop. What can he work out? How many values of h as a function of t, and I put t in bold because there might be a lot of these, different times, to determine the unknowns, which are g prime, nu, gamma naught, v, and s, the shape. Note if he just sees the similarity solution, then he can't ever see the shape, because that's the same no matter what the shape is. So let's see what you can work out. And there are two, well, first of all, you can never work out what the gravity or the viscosity is. You can only work out their product, beta. So you can see a zillion times and do a zillion experiments. You'll never be able to work them out independently. Now, let him see what happens at initially. That's a special case, that'll be A. Well, then he knows the shape, and you'll also let him know something at some further time, not 0, but 0 plus, and you let them see the radius at that same time, which I'll make it very much larger to 0. Then that leads to P, the percentage error at that time t, and you can work out beta, but you can't go any further. If you don't allow the initial condition to be seen, then all you can find out is this combination, beta gamma naught to the 8/3 of A. And you work that out, you can get a zillion different representations of that. A is that parameter, but you don't know what beta is, you don't know what gamma naught to the 8/3 is, so you don't know the shape, you don't know what A is, so you're lost. So it's one of these typical examples where the inverse problem is not unique. So in summary, if you're given the shape, i.e. concede at 0, then all else can be determined. But if you're not given the shape, you don't know how it starts, and there's many other long-term data of which nothing really of importance in the details can be determined. What I'd like to do now is just to tell you a little bit about large Reynolds number gravity currents. I've been talking about low Reynolds number gravity currents, and they are quite different. And that's what I wrote the paper on that everybody thought I should understand. This is a very old photograph by the wonderful John Simpson, who was the first person in some sense to really, no, that's unfair. The first person to look carefully and systematically at gravity currents. I'll talk more about gravity currents later, and it was von Karman who was the first to look at it, but we'll go into that later. So these are the equations, nonlinear equations, and I'll just write them down here. Shallow water equations, all two-dimensional to make it easier. G prime as before, the difference in density between this heavy fluid that's spreading out and this light fluid over which it's spreading. Initially, it's always got zero velocity at the wall here, and you can get a similarity solution that says that it propagates like t to the 2/3 with G prime A and some constant here, which is in terms of the Froude number, the condition at the front here. There is some condition at the front, and we'll talk about that later. Okay. Now the question is, how does the similarity solution with the real solution change with time? This is time, but it's the log, that doesn't matter. And here's the percentage error. For very small time, it's quite high. It goes down and down. How boring, nothing very interesting there. And then it goes back. And it increases. And then it comes to a maximum. And it goes down. And it even gets negative. And then it increases. So whereas for the low Reynolds number flow, this guy always beats the similarity solution. Always, but gets closer and closer and closer. For the high Reynolds number flow, it's quite different. It gets closer, and then it gets further away, and then it gets to zero, and it overtakes, so it's really a good race. And then it goes, now it's true that they have to approach each other, or it wouldn't be a useful solution, but it's a quite different approach. And so there must be a lot of problems. What makes one or the other, I don't know yet what they are, but there must be quite a lot of different problems. And it doesn't go like 1 on p, and it doesn't go like anything simple. It's closer to p to the minus 2/3, and I'm sure there's still something to be done here. But that's really quite a different case. Now I'd like to spend just a little bit of time, gee, I don't have much, talking about what happens if you change the flux. And the reason that I became interested in this, as I'll talk about later, is that there's carbon dioxide that's stored in porous media, and the carbon dioxide is less dense than the interstitial water of this sort of small grain rocks put together like loose sand, but under pressure of about 1 kilometre. It rises to the top, and then it spreads out as a gravity current in a porous medium. And the question is, what happens if, for example, this operator turns the machine off, forgets to turn it back on again for a week or 2 weeks, or he's sick? How long does it take to get back to the similarity solution that it first had? This is now a constant flux. The details of the similarity solution are different, but that doesn't matter. Here's another example. This is a volcano. It's spreading out a viscous fluid that's going down a hill and then more or less straight. But this volcano doesn't spread out at a constant flux. One morning it feels like putting out more, and so there's an increased flux, and then the next morning it says, oh, I've had enough, does nothing for a few days. How long does it take, and in what way does this front react to this change? And the reason why that's important is that you can use the data here to calculate the viscosity. And that's why I first did this problem, because there was some data which said lava domes spread at a certain rate, and I thought I could calculate the viscosity from that. There are two ways you can get the viscosity. One is the way I did, by doing the mathematics at my desk. This is the way my colleague Steve Sparks, now Sir Steve Sparks, does. Behind this heat shield, because it's damn hot, he has a piece of equipment that he sticks into this lava flow, and that measures the viscosity. Let me assure you all, much better fun to do it this way, much better fun. I was very jealous of him, but my calculations did quite well. Let me just say that in that case, if you change the flux, that's a simple case I'm going to do, after time capital T, the time taken for it to get back to the similarity solution, which I haven't told you the details of, but you can imagine, could depend on gravity, on the viscosity, on the initial flux, on n, which is how you've changed the flux. 0, if n is 0, then you've turned it off, but you might increase it by a factor of 2. I might just say the Norwegian government got paid $45 a ton for $45 a ton for sequestering it, because they told what did I say? The Norwegian oil company, Statoil, gets $45 a ton tax break for sequestering this carbon dioxide, because they told the Norwegian government it would cost them something like $55 a ton to sequester. So Norwegian government said, I'll give you a $45 ton tax break. Once they got going, it cost them $10 a ton to sequester, so they still get the tax break. Now the question is, do they always put in as much as they say? Well, I have no idea about that. What happens if they change the rate by an amount n? So what could happen is that the time to reach this new flux depends on the time since it's been going. G, nu, Q, the flux, N, the change in flux, and T since it's first been going. And that's all there is. Guess what? We're going to use dimensional analysis again. It must be proportional to T. Here are the properties, and here are their dimensions. And what that says is that it's got to go like T times some function of this normalized capital T, the time it's been going before you change it by an amount n. Whoops. So that's what you have by dimensional analysis. Then you write down the equations. It's the same equation as before, slightly different conditions. This is saying there's a constant flux for time capital T, and then it goes at nq, so it's changed by an amount n, and n could also be 0. So you non-dimensionalize and you get this equation for which only capital T occurs. But we've just said that there's possibility here, b cubed q, but b cubed q doesn't appear here. So that says it can't be a factor of b cubed q. So there's an example where you've chosen something that you think it should depend on because it appears, but you can non-dimensionalize it out. And so the time to come to this new solution must be linearly related to the time it's been going, and then you change the flux by the amount n. And in fact, I got interested in this problem because for some reason, I don't know, this was obvious to me. I wrote this down and everybody again said, I don't know what I'm talking about. They do that often. They're always wrong, let me assure you. I then did this analysis, and then we had some experiments done. Now, this is the numerical calculation. Here's the difference between the numerical calculation over the radius of the nose, the similarity solution, the appropriate similarity solution. It goes just like that if n is equal to 1, because you don't change things. This is an appropriately non-dimensionalized time, and at that time 1, because that's when we're going to change things, if we change the flux so that it's a tenth, then it starts up here and it goes down and comes here, because the value for this much smaller flux would be a less extensive radius. If we change it by a factor of 8, then there's the exact opposite. It starts up here and it comes down here. Okay. We did some experiments, basically like this. We had a balance so we could measure the amount of glycerine in here. We pumped the glycerine onto a solid surface, and it spread out, and then at the time capital T, instead of doing it at Q, we did it at NQ. And here's the agreement between the experiments and the theory. Look at this. This is when n is equal to 0. So if you turn the thing off, it's really quite different. It then goes from a constant flux to a constant volume, and that's a singular case. So here it goes for smaller and smaller and smaller and smaller n, but you're still letting some get out, and it takes you quite some time before you notice it go to that new solution. But if you turn it off, then very quickly it goes to the constant volume solution, which we talked about before. I'm going to leave that out because of the time. Interesting, the seconds is accented more than the minutes. I'm still going to leave that out. No, well, I'll tell you what. What we've said is that the time to reach this new solution is proportional to capital T, the time it's been going. So it makes a difference whether you turn it off, as far as the solution is concerned, after 10 years or 10 minutes. It's dependent, it must go to a constant which depends on P because nothing else is there. As n goes to infinity, this is just curve fitting, and that value goes to infinity as n goes to 0. As I showed you up there, say it's like 1 on n, you just look at the theory, and that suggests, does no more than suggests, that it should look something like this. This is the 1 on p, so it goes to a constant as n tends to infinity, and this is just a curve fit. Now you can do the same thing by some sort of physical reasoning to say that the volume initially was NQT is what it should have been, or what the initial volume would have been if you'd had it going at NQ all the time. But what the real volume is QT plus NQ of a T minus, a little t minus capital T, because it went at this for time capital T, and then you change the flux so that it's NQ, and that suggests that you can make this statement that the volume after can be compared with the volume that should have been there, and that putting in a factor which turns out to be correct here, we know by curve fitting, so you're only getting a proportional sign here, you get the same thing. And again, you notice that at n equals 0, if you turn it off, that there's a singularity there. Well, we can generalize that for lots of situations. I think that will do. Okay, let's just have a summary. This I've said before. I think that you can determine more about similarity solutions. And really, and I should have started this way, in most papers using similarity analysis, they say after a sufficiently long time, T star, they'll agree. How long is T star? How does it depend on the initial conditions? How does it depend on the parameters? No one in my knowledge or experience has ever looked at that before. I've already shown you this result and the time scale for the various situations. This is for the change in flux. I went through that rather quickly, I'm sorry. It's singular at n equals 0. And from a constant volume to a constant flux, well, that's a change. It looks something like that. That's another situation, and we can evaluate that. But what I would like to say, this I've already mentioned. Sometimes you can go from here to here, and generally the initial conditions are not satisfied. But this equation may not have a solution. And there are lots of situations, and we'll talk about one next lecture. Intrusion into a stratified ambient, like a volcano, the flow of viscous gravity current over porous media, and so on. I bet there are many more. We can write down this, but it's non-linear, And while you have the right number of boundary conditions, there just isn't a solution. That, of course, we're not that familiar with, but it definitely can happen, and it does here. So what I wanted to say is remember that there are at least two families, because I talked about axisymmetric and one-dimensional problems where you can work it out. I think there are other problems, and if you have any suggestions, I'll happily listen. These are the people who are involved, and many thanks to them. John Lister, my one-time student and colleague, who wrote the original numerical program that we used. Jerome, my one-time postdoc and now colleague, who modified it slightly. Thomasina Ball, a summer student, who was funded by James Bridgewater. I think I've told some of you the story. James Bridgewater was a very good student. He did mathematics in Cambridge and did very well. But he decided not to continue with mathematics, and he went into the city and made a lot of money. And at age 40, he said to his wife, you know, there's this very difficult part 3 year in mathematics. I'd like to go and do part 3 and see how I do. Okay. So he went to do part 3. He enjoyed it enormously. He did very well. So he came home after the results and said, I've forgotten his wife's name now, Judith. Judith, I'm really so pleased I did so well. I'm going to do a PhD in mathematics. I'm really so excited. And she said, no, dear, you're going to continue to make money. So he continued to make money, but he was very, very generous and gives us money to support these students over the summer. Old Trinity gave a little bit for Joseph. And Joseph Weber, a wonderful summer student who I had, and I'll tell one final story if you don't mind, because I think he's so terrific. On another totally different paper, which I haven't mentioned that I worked on with him, I said to him, you know, you sent me the penultimate version of the paper. I was in Australia at this stage. You sent it on a scan. And I made 12 suggested alterations. He knows suggestion for me means suggestion. He's in control, he's the main author, but 12 suggestions. When the final version came, 6 of the alterations were exactly as I'd suggested, and the other 6 were very, very much better. I was really impressed. You'd outthought me and made them much better. And he wrote back and said, oh, Herbert, I'm afraid you don't understand. Sometimes I can't interpret your handwriting. That's the modesty he has. Okay, well, that's enough. Thank you very much.